Right now, somewhere in the world, a quantum computer is solving problems that would take classical computers thousands of years. Secure messages are being transmitted using unbreakable encryption based on the laws of quantum physics. Doctors are scanning the human body using advanced imaging technologies that rely on the behavior of subatomic particles. All of these revolutionary technologies are built on one strange and mysterious principle. The act of observation can change reality. This phenomenon is known as the observer effect, a fundamental idea in quantum mechanics. At the quantum level, particles do not behave like tiny solid objects. Instead, they exist as waves of probability, capable of being in multiple states at once. But the moment scientists try to measure them, something extraordinary happens. The possibilities collapse. The particle suddenly chooses a single state. It is as if the universe itself responds to observation. This strange behavior was first revealed through the famous double-slit experiment, an experiment that shocked the scientific world and forced physicists to rethink the nature of reality. Great minds such as Niels Bohr, Werner Heisenberg, and even Albert Einstein struggled to understand what these results truly meant. Does observation simply reveal reality? Or does it actually help create it? If measuring a particle changes its behavior, then a deeper question emerges. What role does the observer play in shaping the universe? And could consciousness itself be part of the equation? In this documentary, we will explore the fascinating science, the groundbreaking experiments, and the revolutionary ideas behind one of the strangest discoveries in modern physics. The observer effect. Modern physics has revealed something deeply strange about reality. At the smallest scales of the universe, simply observing something can change it. This phenomenon is known as the observer effect, a key concept in quantum mechanics. Unlike everyday observation, where watching something doesn't change it, in the quantum world, measurement itself alters the system being measured. This idea challenges our classical understanding of reality and forces us to ask a profound question. Does reality exist independently, or does observation help create it? 2. From uncertainty to observation. The roots of this mystery lie in another foundational principle discovered by Werner Heisenberg. His famous Heisenberg uncertainty principle revealed that certain properties of a particle, such as its position and momentum, cannot both be known with perfect precision. The more accurately we measure one property, the less accurately we can know the other. This limitation is not caused by poor instruments. It is a fundamental property of nature itself. 3. Superposition, multiple realities at once. In quantum physics, particles behave in ways that defy common sense. Before measurement, particles do not exist in a single definite state. Instead, they exist in superposition, a mixture of multiple possibilities at the same time. An electron, for example, might exist in many locations simultaneously until a measurement is made. Only then does the system collapse into a single outcome. 4. The famous Schrödinger's cat. To illustrate this bizarre idea, physicist Erwin Schrödinger proposed a thought experiment known as Schrödinger's cat. Imagine a sealed box containing a cat, a radioactive atom, a poison mechanism triggered by atomic decay. Because atomic decay is a quantum event, it exists in superposition. Until the box is opened, the cat is theoretically both alive and dead at the same time. Only when someone observes the system does the superposition collapse. While absurd, this thought experiment highlights the strange role observation plays in quantum mechanics. 5. The double-slit experiment. Perhaps the most famous demonstration of the observer effect is the double-slit experiment. The experiment works like this. Step 1. Without observation. Particles such as electrons are fired at a barrier containing two slits. Instead of behaving like solid particles, they produce an interference pattern, as if they were waves passing through both slits simultaneously. Step 2. With observation. When detectors are placed to observe which slit the electron passes through, something remarkable happens. The interference pattern disappears. Now the electrons behave like individual particles passing through only one slit. The simple act of measurement changes the outcome. 6. Does consciousness cause the effect? This raises one of the most debated questions in physics. Does the observer need to be conscious? Most modern physicists believe the answer is no. Instead, observation simply means interaction with the environment. Through a process called quantum decoherence, interactions with other particles or measuring devices cause quantum systems to lose their superposition. In other words, any interaction that reveals information about a system can change it. Although the observer effect is strongest in quantum physics, similar patterns appear in everyday life. The Hawthorne effect. In psychology, the Hawthorne effect shows that people often change their behavior when they know they are being observed. Workers may become more productive simply because they are aware they are being monitored. Behavioral changes. Drivers slow down when they see traffic cameras. Students focus more when teachers watch them. In these situations, observation influences behavior, though not at the quantum level. 8. Different interpretations of reality. Quantum mechanics offers several interpretations of what observation truly means. Copenhagen interpretation. Proposed by Niels Bohr, the Copenhagen interpretation suggests that physical properties do not exist in a definite state until they are measured. Many worlds interpretation. Another theory, the many worlds interpretation, proposes that all possible outcomes occur simultaneously in separate parallel universes. We simply experience one of those realities. 9. Real-world applications. Despite its philosophical implications, the observer effect has practical technological uses. Quantum computing. In quantum computing, qubits exist in superposition, allowing immense computational power. However, measurement collapses this state, which scientists must carefully control. Quantum cryptography. In quantum cryptography, any attempt to intercept quantum information disturbs the system. This makes it possible to create extremely secure communication systems. Medical imaging. Technologies like positron emission tomography use quantum interactions to create detailed images inside the human body. The deep question of reality. The observer effect reveals a startling possibility. Reality may not be entirely independent of observation. At the deepest level of physics, measurement is not passive. It actively shapes the systems we study. This idea suggests that the universe might be less like a rigid machine, and more like a dynamic network of possibilities waiting to be observed.